All right. I once again have the Easter cartoon here because, I don't want Indy to miss out on the funny quantum physics joke about Saint Schrodinger, which once again I have to correct it because got to have the umlaut over the O. As long as the tomb is closed, Jesus is both alive and dead. All right, enough of that. Did you have a chance to view the tape or the recording from Friday, Indy?
I have not.
Okay. Most of what we did was looking at spherical harmonics things, I believe. But then we got to looking at the radial Schrodinger equation. Now, in the homework, I'm guessing you guys probably haven't had a chance to look at the homework yet either, have you? No. Okay, well, in the homework, let's look at the homework real quick. There we go. So the first question, under what conditions are spherical harmonics? No big deal there. The second one, I told you maybe once, probably for sure, you would have to do this in the homework, and sure enough, I decided to have you do it. So you have to create the spherical harmonic. You can look it up in the book to make sure you have it right, but you have to show the process of creating the spherical harmonic for the Y22 spherical harmonic. That is L equals 2 and M equals 2. So you have the equations here, and the process is first you make your polynomial, and then you take that and you make another polynomial, and then you take that, so it goes from there to there to there to make your entire thing. And it just involves a whole bunch of derivatives. And it's not hard. The next one is the one I want to, actually it's the last one. I'm just going to go over what each one is, and then we'll get started. The next one, it's exactly what it says. This is our wave function. It's a superposition state of spherical harmonics. And your goal is to find what the probability of a measurement giving different values for L, what's probability of L equals 0, what's probability of L equals 1, what's probability of L equals 2, and so on. And then what's the probability of a measurement giving you different values of M. So to do that, you're going to need to rewrite this as an expression in terms of the spherical harmonics. Or I suppose you could do, y0, 0, psi equals c 0, 0. And you could do all of these, but that would be a whole lot more work. So don't do that. Write this so you're going to have, after substituting the x, y, and z in the appropriate places, you will have psi as a function of theta, phi, and r. Now, notice I put x, y, and z. I do have r here, where r squared is equal to x squared plus y squared plus z squared. Technically, I should have had the x squared plus y squared plus z squared, but it's just extra work and I didn't want to. So you have psi as a function of theta, phi, and r. Break it up in terms of e to the I phi times this, plus e to the minus I phi times this, plus etc. So you'll have all those separate terms and then match up with the spherical harmonics to say, now I have psi is equal to c xy, well, I'll put lm. For all the different L's and M's that are present. And there's only 4. There's only 4 total terms, so it's not like you have a very long thing. And then once you have psi in that form, then you can determine what the probabilities are for each answer. So I haven't done the problem, not close. You probably can't see the end from what I said here, but it should be enough to get you started. Now, the reason I actually wanted to come here was because of this third one, or fourth one, the one that were 30 points. A particle of mass m is placed in a finite spherical well such that v for r less than a, that's inside the well, is 0, and V for R greater than A is V0. Find the ground state solution. So you're only looking for one solution, the ground state, by solving the Schrodinger equation with L equals 0. Now remember, the Schrodinger equation, we had blah, blah, blah equals L times L plus 1. So if you're doing for L equals 0, what's this thing on the right-hand side? 0. So it's making it a much simpler problem. But you are going to actually find the radial solution. And the way to do that is going to be to first find U, find the solution U, and then use the definition that the radial solution is U over R, right? Because we have the Schrodinger equation in terms of U. And then when you find this, you have your answer, and then you have to use boundary conditions to get to that. So apply the boundary conditions, you'll be able to deduce this. That is, you get no solution if the potential energy is less than this value. Has to be at least this big to get a solution. You very well may have questions. I assume we'll be meeting tomorrow?
Yeah.
Yes. Okay, I'm going to try to use the Zoom meeting thing. Do you guys have any experience whatsoever with that? No. Okay, I will try to experiment with it myself some today, and I'll try to see if I can have like Greg Merchant or somebody there tomorrow, so you have somebody who knows how to get it connected up. But that should allow us to use this setup in the room that I'm going to be in. Okay, then getting to today's material. And of course, we're going to have some redundancy here for Chris because we talked about the first 6 or 7 slides, I think, on Monday. So here's that Schrodinger equation in the radial form. Like I said, this here is what we're going to set to 0, and you're going to solve this. For that homework problem, inside V equals 0, outside V equals V0. So you have 2 regions, and you're just going to solve this equation for those 2 regions. But that's not what we're doing today. I call this the hydrogen atom, but we're not really doing the hydrogen atom even yet today. We're just going to be looking at the radial solution initially. So we don't have a defined function V, we just have V in there. Well, the first thing I'm going to do is make new variables. Why make new variables? Simply to make it easier to write. So we define this U is equal to radius times capital R. So U is a new function that's going to make it easier. Now, what I did yesterday Friday. Today's Monday. I'm really up to date on the days of the week. What I did Friday was to show that these 2 equations are equivalent. So I'm not going to go show that again, but they are equivalent equations. And then we define an effective potential that's the actual potential plus this term here that is called the centrifugal term. Christopher asked, why is it called centrifugal term if we know from physics that centrifugal force is a fictitious force? And my answer was, this is a potential energy that has to do with, in order to go in a circle, it would appear like you have something pulling it out, a centrifugal force that you have to put a force inward. Of course, that's not really the case. What's really the case is it wants to go in a straight line, and you have to apply a force toward the center to make it curve into the circular form. But that's why it's called the centrifugal term, because it's the term that if you don't include that, it's just going to travel in a straight line. Or a straighter line, I should say. So this here was an important change because it makes the equation simpler to write. We replaced everything that was in this that bracket, with a single constant. So now I can write the equation here as I can write it as that, or I could have moved the other side of the equal sign. But that's much simpler to write, right? The V effective is much quicker than writing out all the stuff that was in the bracket. That's why we do it. Oh, look. Shoot. Nothing to see here. This here is that problem. We won't do this solution here because that is the homework problem, except for this here is general for any L. And yeah, we made the L 0. If and only if L is 0, yeah. Going past there, you still have to show the work. That just showed you the answer. For the hydrogen atom, so now we're getting to the hydrogen atom, our potential function is K E squared over R. In my work that's going to follow, I'm not going to use K because we use K often as that exponential term, and I don't want things to be confusing with two Ks in there. So I'm going to use this form throughout just to keep it straight. So here's the Schrodinger equation. Of course, this whole thing was the V effective. But now I have one that's 1 over R and one term that's 1 over R squared. So there's some interesting R relationships in here that I'm going to have to deal with. Defined kappa as square root of minus 2me over h bar squared, which means that this here is 1 over kappa squared. Or I could have rewritten the equation as, well, what we have right here. Yeah. So I could have written the equation like this now with that kappa definition. But we go a step further and define yet another variable, rho. So instead of radius r, now we have rho, the Greek r, is kappa r. And then we have rho 0, another constant, 2me squared over 2 pi epsilon 0 h bar squared kappa. It seems that we're doing a lot of fluffy work that's not getting us toward our answer. But what we're doing is getting it down to an equation where you can actually kind of see it. So now our differential equation is a much shorter to write equation. The second derivative of u with respect to rho squared is equal to 1 minus rho 0 over rho plus L times L plus 1 over rho squared, all times u. Fairly simple equation. Not a simple solution, but a fairly simple equation. Now, at this point, based on your experience in quantum physics to date, what would your method be to solve this? And of course, we can look at Christopher if we want because he's a math major, but fact is, both of you probably have similar ideas. And they might be, as Chris just indicated. How would you solve this?
We'll separate the rows and the U's. So get U's on one side, rows on the other side. Separate.
How would you feel if I told you that is not possible? That would be a good idea, but it's not possible. That would be the perfect idea.
Wait, why is it not possible?
It's not possible because you have 3 different powers of rho in these different terms.
Oh, yeah. Okay.
So I circled the u's and then I did the rows. You know, you multiply by rho. Well, I got rid of rho in this term, but now I added it to. Okay, you can't see what I was doing. Multiply by rho, you get rid of rho in the second term, but add it to the first term. Right? It's not an option. If it was, that's what we would do and would be done. Okay, another idea. Find solution for a specific case. Think back to what we did before, simple harmonic oscillator.
Far away.
Yes. Okay, so rho being very large, if rho is very large, then what is 1 over rho squared going to look like?
0.
What is 1 over rho going to look like?
0.
And so this equation becomes now we're talking. We can find a solution to this. What's the solution? What's the form? Once again, not assuming that you have your differential equation straightened out. What's the form of this?
Yeah, so.
Yeah, e to the something rho, right? And then we take the second derivative, put it in, and we're going to have so what is b going to have to be? Plus or minus 1. So that means our solution is, and I'll call this, I'll call it U1. Just, it's for the special case of very large rho. Okay, my colors are not making me happy. Now we have to check to make sure this is going to be normalizable, that it's going to function right. In which range of rho is this valid? Very large. So in the limit as rho approaches infinity, this needs to not blow up. What does that require? Right. A must be 0 so it doesn't blow up. So our U1 is B, some normalization constant, e to the minus, and I don't know why I put B there. We just learned that B was plus or minus rho. Don't have to put a B there when we know it's plus or minus 1, or yeah, B was plus or minus 1. Okay, so that's simple enough. That's our long-range solution. Now, what we did before, after the long-range solution, what did we do? Then we did what?
Find the complete solution by finding the. Yeah, we multiplied it by an infinite polynomial.
Right, we multiplied by an infinite polynomial. This one here is slightly different. Why is it slightly different? Because in that one, we had only going from plus infinity to minus infinity. Now we're going from 0 to infinity. And so we're going to make a solution that's in the short range first. So this is our long range solution. Now we're going to find our short range solution. So here's the long range solution. So turning to the short range solution, if I come back to the differential equation for short range, for rho is small, then 1 over rho squared is much bigger than all the other terms. And so for the short range solution, I just have the term that had 1 over rho squared. And that one there, differential equation, you just basically have to use your polynomial rule from differential equations class. and you find that there are two solutions. One that's, well, let's just check this, right? Because we're not differential equations class. I know you're in it. You probably have done this, but just to check it, whoops. My C looks like an L. So that's what we get when we do the second derivative. And so we notice this term here has the L times L plus 1 and rho to the L minus 1. If we look on the other side, it would have been L times L plus 1 over rho squared, which is going to lower it from L plus 1 to L minus 1. So that term is a solution. And then this one here, again, minus and a minus, that's a plus L times L plus 1. And rho to the minus L minus 2, this term here, L times L plus 1, rho to the minus L over rho to the 2 is rho to the minus L minus 2. So indeed, those are both solutions. But only one of them works. Which boundary is this one going to be looking at?
The 0.
As rho approaches 0, what happens to the first term as rho approaches 0?
It's just rho to the 1.
0 to the L plus 1, it's 0 to any power, it's going to be 0. What about rho to the minus L as rho approaches 0? Is what?
We're looking at L, not rho. Yeah. So when you said
Did I say L instead of rho?
Yeah, we were.
My
I
mistake.
think we're
Rho. As rho approaches 0, what happens to the rho to the minus L?
It goes to infinity.
Yeah. So that means D has to.
Be 0.
So that means our solution for small radius is this here. Our solution for large radius was this here. And so our overall solution, now we're going to do, okay, let's use an infinite polynomial to finish it out. So here is our large radius solution, or our small radius solution. Here's our large radius solution. And then here is, and we just took the normalization constant out and said we're going to put the normalization constant into the polynomial. So that's got to be a solution. But we need to test it to see how it works as a solution. Now, one of the first things to note is an infinite polynomial. How does an infinite polynomial compare with an exponential as rho approaches infinity?
Well, the exponential. Well, in that case, it's going to go to 0. In that exponential.
Yes, but what we have is rho is going to infinity, e to the minus rho is going to 0. Which one's going faster? the answer, if you look at the textbook, it gets a little weird. Let me just point to where it is in the textbook where he does that. He says, let's say that this function is approaching this, and you're like, why? That's weird. And then he has a subscript, so you read, a footnote, and you read the footnote. He says, this may seem weird, but it makes it easier. And so, if you look at page 148, he's actually doing this with the, starting with the solution a little bit further on. And you see footnote 14, you might ask why I don't drop the 1 in j plus 1. After all, I'm ignoring 2 times l plus 1, saying that's approximately 0, but not 1. And he says, well, it's because it makes it easier. But what he's doing is showing a mathematical proof that in the large radius limit, that this here is going to be proportional to e to the 2 rho. So he comes to this later on. But if you have an infinite series, it is exponential, and it comes down to what is the power of the exponent to compare the two. But the infinite series would be e to the 2 rho. E to the 2 rho times e to the minus rho is e to the plus rho. It blows up. So this blows up if it goes to infinity. And so we change it from going to infinity to n. We say that it has to terminate at some value n. Now, we don't actually erase it. We just it turns out that c for j greater than n is equal to 0 in that series. So the series has to terminate if we're going to have a solution. So every solution has to terminate at some value n. That's actually our principal quantum number n. That's the number where the series terminates. Now, we haven't gotten to that, but I just want to point it out now because, well, now seems like a good time to me. So what are we going to do? How are we going to test to see anything about these coefficients c sub j? And we have experience from this. We're not working in a vacuum. How did we do it before? Okay, we look back at the Schrodinger equation. I think this is what you were saying, Chris. It wasn't quite loud enough for me to be sure.
If we put in a recursive relationship by plugging in with the derivative.
That's right. So we came to the Schrodinger equation. So here's the Schrodinger equation complete with a plus sign in the middle of it. So we came back to the Schrodinger equation. So here I have our substitutions in the Schrodinger equation. Here's our solution. We're going to put that in. And so that means I have to take the second derivative of this function. So let's start with the first derivative, of course. So, mathematician and physicist, what's the first derivative of this function?
Okay, so we got the product rule, so it will be rho to L times e to the minus rho. L plus 1, yeah, you know what I'm saying.
I'm with you. Okay, so there's one term. Sorry.
So we have negative. So you bring the negative up from
Good enough.
the exponential, and then so you have negative e to the negative rho times rho. Yeah. Oh, you just put up front. Never mind. Yeah.
And then what? Then my, and last but not least, I'll do the last one because I'm that kind of guy. There we go. We did the product rule 3 times. Well, 3 terms. So there's our first derivative. Now we have to do the second derivative. So, Indy, take it away.
So we got L plus 1 times L, and then times rho to the L minus 1, times e to the minus rho, times v to the v.
You know, I'm going to stop putting that. It'll make my life simpler. That's term 1 of 9. What's next?
Now we're going to do it with respect to e, so you can bring the minus, and then you have your L plus 1 rho L to the
And last of all, okay, there's the derivatives for the first one. Aren't you excited? Yeah. I'm just thinking that, you know, Christopher's got to be saying, yeah, this is exactly what I signed up for with a math major.
maybe on a good day, but right now I'm pretty foggy.
So there's the first one, second one, third one, and we get to the final one. Now to combine terms. So notice that we have, let's see, derivatives, single derivatives. Single derivatives appear here, 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 and here. So we have 2 of them that are plus L plus 1 out front, 2 of them that are minus, and with nothing out front but rho to the L plus 1. None of those add to 0. Wah, wah. Actually, I'm going to put the highest derivative first. And then I've got the last one. Again, 4 terms. Is it 4 terms? 1, 2, 3, 4. Yeah. And I have L plus 1 L. Oh, goodness. These 2 here are the same factor out front, and they're both negative. Would you write this a simpler way? I think we really should. Notice we have e to the minus rho that can be pulled out of every single term. And we have rho raised to a power of L plus 1, L or L minus 1 in every term. So we can pull out e to the minus rho because that was in every term. And I'm going to take out a rho to actually the L minus 1 from every term. And so then my first term is rho squared d second v d rho squared. Right, to get to rho to the L plus 1 from rho to the L minus 1, I have to multiply by rho squared. And then my next term, this one here, I'm going to have to multiply by rho. The next one, I'm going to have to multiply just by 2. And then the last one, this here rho squared, this one rho, and that one just factor. So
shouldn't it be a rho squared by that 2?
a rho squared by that 2.
And sorry, in the second term by the dv, the first derivative. Here, because you took out L, rho to the L minus 1 out of rho to the L plus 1.
You're saying this term?
No, sorry, the next term by the first derivative.
2L plus 1.
Well,
Okay.
actually the 2, it's the regular 2. There should be a rho squared there, right?
Oh, yes, yes. You're right. And likewise, I did them wrong here as well. So and okay, so L plus 1 should have a rho squared anywhere there's L plus 1. Okay, so there should be rho cubes for those terms, or rho squareds. Yeah. Okay, I think I have it right now.
Yeah.
Well, that is really a nice second derivative, isn't it? I say that fully tongue-in-cheek. So, how do we go from that to getting something like this? Right? There's this recursive relationship that is given in the book. I don't recall did it. Let me look here to see if they actually did the hard work on this. Did they? Yeah, they did do this. If you look at the equation between 4.60 and 4.61, the right one right above 4.61, that's the second derivative we just did. Hopefully it looks the same. Now what's different is, of course, I did this bullheadedly. I wanted to do it myself and not, like Frank Sinatra, do it my way. They factored out a row to the L, and so they have one term that's a row and one that's a 1 over row. Fundamentally, it doesn't make a difference, but they did it differently there. And they multiplied through what these terms are. And so if I multiply that through, they don't, first derivative, yeah. So they put it like that. And so you can see that is the middle term in their equation, 2 parentheses L plus 1. Minus rho. Do I have, apparently I have a sign wrong. Yep, that sign right there. It's correct there. So that's that one. And then the lower one, expanding it out. And, boy, actually, they didn't do it all the way out. They left this as is. And then this they put as 2L minus 2. Yeah, so they obviously the textbook form is probably the most convenient form, but they just took this here and wrote it as so they did it like that essentially. So we had one mistake after you corrected my other mistake, and that was the minus sign that I wrote here.
Out of curiosity, where did the row 0 come from in the E term?
The row 0 right here. What are you talking about?
So,
I'm-
4.61, they have the last term as row 0 minus 2L plus 1. Where did the row 0 come from?
Okay, so yeah, so following what the textbook has here, the equation that we just found, which, yeah, we've gone through and shown that it's the same as that intermediate equation. They then take that and say, okay, if you go to the Schrodinger equation, so you go up to here, and that's this side of the equation. And that's equal to this. And so this has the row 0, and that's where the row 0 is from. So I'm looking at the time now. We have 3 minutes left. The next step was to take this second derivative that we've done and set it equal to 1 minus rho 0 over rho plus L times L plus 1 over rho squared U. And so that gives you the equation, and I'm just not going to show that work because it's a little too long. Instead, we have the equation that says rho times d second v d rho squared plus 2 times L plus 1 minus rho dv d rho plus rho 0 minus 2 times L plus 1 v equals 0. And I say, okay, now we can take our V function right here, dV d rho is equal to that. And likewise, d second V d rho squared is equal to so we can make that substitution. That goes there. And that goes there. And of course, the V is going to be substitute our original. And now we're going to have a summation in each one. And for just like before, I think we need to shift our indices. Yeah, you can see the bottom of page 147. It has the dV rho is equal to what I wrote. And then says, well, we can rewrite this as the sum of j equals 0 to infinity C sub, and it's j plus 1. So we change the index by 1. So that means it's going to be C sub, and then it's going to be j plus 1. I don't have space to write it. But shift the index by 1. So if you shift it by 1, you're starting your index a different place, but you have to make sure that you're still starting from a power of rho to the 0. So if it's rho to the j minus 1 and you started at 0, you actually would have been starting from rho to the minus 1. But of course, you don't get rho to the minus 1 from an infinite series power series. It's going to start at rho to the 0. So this is a very legitimate move. You're removing a term that shouldn't be there. It's a term that when you bring down the j, it's bringing down a 0. And so it's shifting the index by 1, and the second derivative likewise shifts the index by 1 if you look at the top of page 148. And then you put those into this equation that I have in magenta. And so when you put those in, then you're going to get the long equation that's shown in the middle, well, let's say 2 inches down on page 147. Because we're out of time, we're past time now, I'm not going to write it down, but you get that long equation, which gives you, it's got to be true independently for every j value. And if it's true independently for every j value, it just gives you this recursive relationship. So we've gone through math like that before. I should go and add it to your homework problem now, say, show how it gets there. Yeah, I'll save that for another homework problem. Yeah. But now we have this recursive relationship. And then for it to terminate, we're going to set a termination condition, but I will just start there in class on Wednesday. All right, so like I said, I will try to make sure Greg can be there to help you tomorrow or something so we can use the classroom system and hopefully have a better experience than we did last time with the tutoring.
Okay.
All right, I'll see you tomorrow.
I haven't looked at any class, but is the test grading? Is test graded?
It's not graded. I did the solution to it and was going to grade it last night, but it was last night. And it's good that I didn't, because I realized this morning, hey, I forgot to say what makes it a valid solution. What does make a valid solution for an operator, or what makes an operator valid for quantum physics? Did you guys have a hard time answering that, or did it come right to you? Okay. The answer is it has to have real eigenvalues. And I forgot to put that in my solution. So it's a good thing I didn't go and grade it, right? But well, the eigenvalues are the observables. So
Well, yeah, but real observables.
yeah.
Which is what?
Yeah, which would be fine. If you put it has to have real observables, I'm going to mark that as correct. All right. I'll see you.